All right, thank you for staying for the last talk before lunch. This is about our ongoing project on Remap. You can see the team. Bojan and Matthias are on the back. Also Cosmin Petra from Lawrence Livermore, and Brendan Keith and Doyan Kim from Brown University. So generally, Remap is about moving data between computational domains. In our case, two meshes. We have starting mesh with some field, and we have another mesh, usually a better quality mesh, and we want to move the field from the starting mesh to the other with some requirements. This example has meshes with the same topology. It can be different topology. It can be other things like just representing data on a mesh, projecting, reconstructing data on a mesh, and so on. Our use case, our goal is the AO framework because the project is funded by Lawrence Livermore. That's what they're interested in. But you can use it, as I said, for many different things. Generally, transfer of data between different codes, different representations, reconstructions, projecting data, and so on. And of course, the interesting part is that you always have some requirements for this remap or projection. The requirements in our case, again, they are customized for the shock hydro, but they're quite general. You can see that it can be translated to other situations. In our case, we want to be accurate and sharp, of course, minimal numerical diffusion, especially for multimaterial simulations around interfaces. That's the main focus. You want to be conservative. In our case, volume, mass, total energy per material, and momentum. You want to usually to conserve some bounds. You don't want to jump and get non-physical oscillations because of the remap. And when you have a multi-material simulation, you usually get some material consistency requirement. For example, volume fractions should sum to 1 at every point, not to create holes or things like that. I have this slide. Usually people, and we used to do it with advection-based methods. When you have two meshes, you usually define some pseudo time where you advect your field from the new mesh, from the old mesh to the new. And this is nice because you work with PDs. We like that. You can put theory, you can put physics. You usually define these flux forms where you are conservative because whatever goes from one place goes to the other. But that's where the nice things end, and it starts to become difficult once you go into the requirements. First one, as I said, we get direct conservation. Then when you want to preserve bounds, things start to become nonlinear. You introduce limiters, Fox-corrected transport, other techniques. People have done that for a long time. We know how to do it. We've done it. Then the next one is sharpness. And when you go down for every new requirement, you want to keep the previous ones. Of course, sharpness becomes more tricky. You need to introduce things like anti-diffusion. Becomes very nonlinear when you have CFL restrictions that hits you right away. We spent a lot of time developing techniques that are bounded, sharp and conservative. We have papers about that, but it is difficult. It's very difficult to get all of that right. And the last one, when you go to the material consistency, we simply don't know how to do this, and I don't think anyone can do all this with a advection-based method. And there is one more requirement that I'll talk later that people don't at all think about that because they're stuck here. So yeah, in general, remap, the remap step, when you have some simulation that involves remap and other things, but the remap step is the main source of error in these simulations. Okay, so now I'll show you what our problem structure is. It's just to give you an idea what the requirements are on more technical level. These are for AO hydro, but you can see that when you have other contexts, it will probably be something similar. So in our case, we have These volume fractions eta, raw densities, E energies per material, and some velocity field. Okay, here is the material index. The sharpness means that once you have your original fields, you want to be as close as possible to the original fields. Then the conservation, these are global integrals. They can couple your fields. They can couple fields inside one material or across the materials. As you see that sum there over material for the momentum. And they can be linear or non-linear. But there are few of them, just 4, they're global. Then you have the inequalities. These are per degree of freedom, not coupled, but they're at every degree of freedom. And finally, the coupling requirement, sum of eta k equals 1. This is at every degree of freedom, and it couples across materials. So you see, it's a mix of equalities, inequalities, linear, non-linear things, local, global, and so on. So this is what we want to be able to satisfy all of this at the same time. The approach, we have a 2-step approach. First, we will get a very sharp guess with GSLIB, direct GSLIB interpolation in physical space. This avoids advection and things like that. It's straight going from the starting mesh to the final mesh. This is sharp. This is the sharpest you can get, but it's not conservative. And then the second step will be to fix the conservation while having all these properties from the previous slide with some kind of optimization. Oops. Sorry, pressed something. Okay. Optimization. We have two optimization solvers we're working on with. First is the interior point methods by HiOp. HiOp is a library that's developed at Lawrence Livermore. And then we'll also try the latent variable proximal point by Brendan Keith and Doyen Kim at Brown University. I will explain why we want to try the two and what are the main differences. The main difference is how they handle the bound constraints. And as I said, this will be a one-step sweep, which is good in certain contexts. For example, for AO, when you have big displacements, you usually advection gives you some issues for that. Okay, the step one, the initial guess with GSLIB. This was discussed several times in other talks. GSLIB just given a point in physical space, it can find where it is on a mesh, what the value is. It handles the parallel communication and so on. It is sharp. You get exactly the value you had on the starting mesh. It is not conservative. It is in bounds because the way you define bounds, you get a value that is in there. You usually get some neighborhood, but you get the exact value, which is always in bounds. And the summation to 1 will be preserved as long as it's true on the initial mesh. Once you have the GSLIB, you want to optimize to fix the conservation. The first approach, interior points, we form this objective. So f of x is what will give you the sharpness to be as close as possible. Then you put Lagrange multipliers for each equality constraint. There are a few of them. And you put these weighted log barriers for the inequalities. Interior points, you use the fact that you start in bounds. The bounds gives you this admissible region there. And these two parts give you the directions. So you move in your region until you find the optimum. That's the main idea. The difficulty will be this constraint summation to 1. For now, we We have not started working on this, but we have some ideas. I will not go into the details now. The second solver, the LVPP, it's a new solver by Brandon. There are already some examples of it in MFEM. For our purposes, we will form a similar objective. Again, the sharpness and the Lagrange multipliers are in, then this h of x, it has a similar structure, some log terms that depend on the bounds. But then the steps are a little different. First, we form this sequence of solutions. This is an equivalent formulation. You just solve it iteratively. And then the big trick is that you actually move to this latent space with a transformation that guarantees that in the latent space, you can work in minus infinity, infinity, so no bounds constraint. But when you go back, you're always in bounds. That's the main trick here. And when you're in the latent space, you can, for example, you have more freedom to do things like that. You can force the summation to 1 to be true. And when you go back, you're guaranteeing to be in bounds, which was the main issue with HiOp. If you force this, then you can violate the bounds. So this is the main promise of the LVPP method. Okay, so these are we have this, and I'll go into the results. Now, the first thing one does is just testing on scalar remap. In this case, we just have the eta. We want to minimize this subject to conservation and bounds. We will remap between these two meshes. This is the standard toy benchmark. You have the initial condition on the nice mesh. If you do advection, you can do advection. You get this solution. This is state-of-the-art advection method. You do 256 RK3 time steps. You get some conservative solution up to the order of the time integrator in this case. And then you do the optimization-based one. It is also good. You cannot see a big difference. First thing you see, it's much faster because you do a single sweep. You don't have to go through a time integrator, limiting, and so on. And the error is much better. It's exact because you hit it as a constraint and you can satisfy that. Now, the main selling point in our case is the sharpness. If you turn on the log scale for this, I mean, the advection solution is really a state-of-the-art. But for this kind of remap, I would argue that advection is not so appropriate. The advection, you do a finite element solve on every Runge-Kutta stage. This can introduce diffusion by itself. It's just the nature of finite elements. You propagate. So if you turn on the log scale, you see that actually your material, let's say material, can propagate throughout the mesh. Even if you do things like anti-diffusion sharpness, you can improve this a little bit, but it will still be present. While this interpolation method by design, you just interpolate. So by design, you can propagate at most one layer of elements. All right, this was that. In 3D, it just works in 3D. You don't really do anything because it's optimization based. You just work with the vectors. Observe the same. Advection is 68 seconds compared to 1.9, 1.2 with exact mass for HiOp and LVPP. Smooth solutions, of course, one is to check the convergence. What we do is we interpolate on this final mesh. We have a smooth field. First, we interpolate. That gives us wrong mass. Then we define the bounds with some neighborhood. The interpolated solution is in bounds by design. And then we run the solver to get a mass correction. This is what this test does. So since you are in bounds originally and your interpolation is known to be high order, you would expect that the optimization won't do much. And that's the case. That's what happens. The idea here is to verify this because people usually ask, but you see that for Q2, Q3, we pretty much always get the same L1 error, small differences that in these two cases, but the rate is the same. The mass is fixed almost always to machine precision, and this does not affect the rate. We get third and fourth order in this case. And a note, of course, that with limiting type techniques, for this type of peaks, you usually get the clipping and you're limited to order 2, order 2.5. One thing is with this we can remap directly quadrature functions. So functions defined at quadrature points. With advection, one cannot do that. One needs to project to finite elements, advect, then go back to the quadrature points and so on. With this, there is just a small trick that to define the interpolation. I won't go into details, but there is a way to interpolate a quadrature function efficiently. And from then on, the optimization is just the same. It works on the vector of values to force the conservation and the bounds at the quadrature functions. See your results. All right, once the scalar equations are done, one goes to the system. The first system is just taking the volume fraction, density, and energy before the full problem. In this case, we have the volume fraction is a quadrature function, the density is a quadrature function, and the energy is L2. These are the conservation and the bounds requirements. One note here is that while we remap this, we want to conserve mass and internal energy, which is like a product of fields. We don't have to form these product fields, which one usually does to define his PDEs, conservative PDEs. So again, we save projections and things like that. And we evolve the primal fields and we force the conservation on the products. This slide it's not very high quality picture, but it just shows that it works. Everything is moved sharply and the bounds, the conservation is down to machine precision and the bounds are satisfied. And okay, I will not talk about this. This is something, some specific case preservation of constants, which is important in the AO framework, but I will skip this. Main point is that it gives very good control over small values of the volume fractions. You get what you expect. I will spend more time on this now. So when you remap these systems, you usually have derived quantities. In this case, pressure, and these are very important. In our case, pressure is what controls the velocity. So if it controls the velocity changes, if you mess up the pressure, your simulation will be wrong. Usually when something goes wrong, you first check the pressure. Now, in this test, this is the set-off test. You start, this is a shock wave going out starting from the origin. We stop here at some time and then we remap. We remap density, it looks great, looks the same. It is conservative, it is in bounds. Same for internal energy. Pressure again is a derived field. This is a single material simulation. So if you look at the pressure at your starting state, that's your pressure on the starting mesh. You remapped everything, great, you satisfied everything. You compute pressure from those two fields, you get this mess. Which means that if you continue your Lagrangian simulation with that pressure, all kinds of things will start happening and it will fail. So this is the problem. What do you do when you have a field which is not in your primal variables, you don't remap that directly. But if you mess that up, you're still not good, although you satisfy everything. So this is an additional requirement actually to all the requirements I mentioned on the starting slides. You must control derived nonlinear fields. In our case, it's quite clear what to do. It comes naturally. You just take the starting pressure from the starting mesh. You can interpolate that to get a pressure, to get a notion what should be your correct pressure on the final mesh, and you just add it to the objective while you still optimize for your primal variables. So P star is the interpolated pressure on the final mesh. P is your new pressure on the final mesh. And when you do that, of course, you have to play with the weight a little bit. That's still not completely clear, but the idea is that this way, with this optimization, naturally, you can control derived fields, and you can see that that's much better there. Okay, and finally, the full system, the full hydro system with velocity, momentum, total energy conservation. Same idea, just the velocity comes as a H1 vector grid function in addition to the quadrature function and the energy. And this is the triple point. We run just to time 3.5, Q3, Q2. And then we do a single L step at time 3.5. This is the volume fraction at quadrature points, the mass, the internal energy, and velocity magnitude. Everything you see is conserved to machine precision, and it works well. One issue that may come up, we're still not there, we need to see what will happen. First, you see some pixelization of the interface due to the quadrature point remap expected. Basically, if you have a diagonal line and you want to represent that with quads, same issue. The other thing, so it remains to be seen how that will affect the simulations. In our case, the other thing is that it might be too sharp. There are models that, like closure models, things like that are sensitive to such things. So if you have a zone where you quickly drop from 1 to 10 to the minus 10, 10 to the minus 12, you would probably have to work to increase the robustness in other parts of the code. Okay, in conclusion, this optimization formulation so far looks very promising. We are getting good results. It seems fast, sharp, and so on, scalable. It's parallel. As in future work, we will continue with this summation to 1 and more practical tests. Thank you.
Why is the the functional that you're describing for the derived quantities, why is that interpolated and not on quadrature points? And why is that not a constraint? For the second question, I might have an answer myself, but
why is it interpolated? It is computed at quadrature points. What
no, in the next slide. Yeah, you're saying the minimization over this functional, the pressure is a derived quantity, and that is incorporated as an interpolated quantity on the L2 norm.
Mm-hmm.
I can see why it's interpolated because you're choosing the L2 norm. Is there anything that would hold you from doing that on quadrature point level?
It is at quadrature point level.
Okay.
It's not big L2. It's small L2 norm.
Okay. That's the confusion.
Yeah.
Okay,
Just wrong. Yes.
Great. Are there any other questions for Vladimir? So one option maybe here is to, instead of requesting closeness in the L2 norm, is to just derive bounds from the original pressure and enforce it. Is that something you think will work as well?
It might work, but that would be more expensive, I think, because you would have bounds at every quadrature point, and you have to differentiate at every. It will be more constraints, while this is just goes in the objective as one term. It's an option. Yeah, we can do that.
I mean, for density, you do get bounds and you transfer them, I guess, to the new mesh, right? From the old mesh.
Yeah.
So that will be kind of a,
yeah.
you can do the same for the derived quantity, I guess. Isn't it pretty much already there? You just.
Well, you still have a nonlinear function that you put bounds on, so you have to work more, but maybe that's an option.